I am very delighted this evening to introduce to you a very important concept in chemistry, and this concept or topic is called electrochemistry. And in just few words, this topic refers to the study of how chemical reactions can generate electricity as a type of energy, and how this electricity or this electric current can cause chemical reactions. I repeat, how chemical reactions can generate an electric current or electricity as a type of energy in an electrochemical cell, or how an electric current or electricity as a type of energy can be able to actually cause different chemical reactions. And of course, at the anode and at the cathode as electrodes or terminals in a cell. I'll not be able to dig deep into this topic. I only want to focus on a very important area in as far as this topic is concerned. And what I'm going to look at is a cell. And of course, a cell can have an arrangement of what you call an external circuit that can actually involve the wiring. So you can use what you call a metallic wire to actually form the external circuit. We can have a voltmeter to determine the amount of voltage. You can have an ammeter, you can have a milliammeter, and all this, and even a galvanometer to just detect the flow of current and be able to record the amount of current flowing through this external circuit. And basically, you may also be able to have what we call terminals or electrodes. There are majorly two. We have what you call a positive terminal, or what you call the anode, and a negative terminal, or what we refer to as the cathode. And on top of this, we also need to have what you call an electrolyte. An electrolyte can be a salt or just a compound that can allow current to pass through it in its molten state or aqueous state, so that the current can cause chemical reactions and as well allow the flow of current. And in most cases, in any arrangement that can involve the ammeter, the ammeter, the voltmeter, the galvanometer, the metallic arrangement, and of course the electrolyte, we may also include what we call a bulb. A bulb can confirm that the current is flowing when the circuit is closed. And whatever we may use to close the circuit must be a conductor of electricity. So you might have this one as your arrangement in as far as a cell is concerned. Just to briefly explain to you what this all means, and this may be my simple arrangement that may get used to actually explain to us what this has to all involve. So you might have this, and I've said you can either have a voltmeter, an ammeter, or a millimeter, or a galvanometer. In this arrangement, it doesn't matter. You can have this as you are. So we may actually be able to have this as our electrolyte, and this can be a salt or a compound that is ionic. This must be either in molten state or in an aqueous state, such that it will actually end up having mobile, free, or delocalized ions. So this is going to be our electrolyte in its molten or aqueous state, such that we do expect it to have free or mobile or delocalized ions. And the free, mobile, or delocalized ions can be able to help in the flow of current, or can be able to allow current to pass through them. And I can decide to take this to be my negative terminal and this to be my positive terminal, or this can be my negative and this can be my positive. So I can take this to be my anode, or rather my positive terminal, the anode or my positive terminal, and I can decide to take this to be my cathode or my negative terminal, I can be able to have this as my voltmeter to just record the voltage passing through this external circuit. So this can be a metallic wire that forms the external circuit, and this can be what you call the switch. And you can have cells at the moment. You can be able to have the cells here. So this can be the cells or the cell. So this can be a very good example that can give us an arrangement associated with what a cell can actually consist of. I've talked about a container that basically can be able to actually carry our electrolyte, and our electrolyte can be a salt or a compound that can be ionic, and it must be in its aqueous or molten state so that the ions in it are mobile, free, or delocalized to allow the flow of current through this compound. The positive terminal electrode of this arrangement can be able to get called the anode. And of course, the negative terminal is able to get referred to as the cathode. And of course, this must be able to include a bulb that must actually be able to light, confirming that the current is passing through this arrangement. And the voltmeter can be able to allow us to record the amount of voltage passing through this cell arrangement. The cells are here to actually be able to provide the right energy to drive these ions through this circuit so that the current can be able to flow. So the cells provide the required potential energy, or the energy required to actually drive the ions through this arrangement, allowing the flow of current. And of course, our aim was to look at the types of cells. And in as far as electrochemistry as a topic in chemistry is concerned, we have three main types of cells. Number one, we have what we call a primary cell, and we have also what we call a secondary cell, and lastly, we have what we call a fuel cell. We may have so many types of cells in our environment scientifically, but we shall focus on these three, and majorly for today's class, I'm going to focus on the primary cell. And just a brief explanation of these three types of cells is that a primary cell is non-rechargeable, so it cannot be recharged, cannot be recharged. This is a cell that you cannot be able to recharge. So once the cell has been used, the cell is normally discarded or thrown away because it contains chemicals, and once all those chemicals are consumed and there is an exhaustion in the use of those chemicals within that cell, the cell can no longer be able to get recharged, so the cell is normally thrown away or discarded. But a secondary cell can be recharged, so it is no longer discarded. The cell can get recharged, and that can actually be able to make it be able to get a better chance of getting used widely in our environment. A fuel cell will maximize on the use of hydrogen gas and oxygen gas, and this can continuously be able to supply an electric current once these two very important raw materials are supplied or fed into this cell. So once hydrogen is fed into this fuel cell and oxygen is as well fed into this fuel cell, it can continuously be able to supply an electric current as a source of energy. And of course, this fuel cell cannot practically be able to store energy, but the supply of current as a type of energy can only be able to get taken care of if these two very important gases are fed into the cell. A secondary cell can store energy. Once recharging has been done, it can store energy. And of course, it normally uses hydrochloric acid if possibly there's an absence of what you call sulfuric 6 acid. But majorly, the main acid used in a secondary cell is sulfuric 6 acid. If someone asks you to name the acid that is normally used in a secondary cell, you'll obviously be able to mention concentrated sulfuric 6 acid. And of course, very rarely will you find hydrochloric acid. And I will actually want to use the word rarely. So very rarely as a phrase will you ever find hydrochloric acid getting used as an electrolyte in a secondary cell. So 99.99% of individuals or users or consumers in our environment will utilize concentrated sulfuric 6 acid as the electrolyte in these secondary cells, which normally get recharged. So let's take ourselves to what we are supposed to discuss today. And whatever we want to actually cover in today's class is this primary cell. And to begin with, I've told you that this primary cell can be recharged. No, cannot be recharged. So non-rechargeable to mean cannot be recharged. So to mean discarded after use. You can't use a primary cell and use it and use it and use it and use it and use it. Once you have actually used it and all the chemicals are exhausted, then that means the cell can get removed from the electric device and be able to get discarded or thrown away. So, and where can it be able to get used? This cell can get used in one, areas such as torches, watches, clocks, we have what you call flashlights, we have what you call electric bells, electric bells, we have radios, and even calculators that are normally used in accounting or in mathematics as a subject. So torches, watches, clocks, flashlights, electric bells, radios, and calculators can be used. And they can actually be able to get used when these primary cells are available. And of course, even the remote control we use in our homes can actually be able to actually utilize the use of these primary cells. So if you look at this cell, it actually looks like this. Okay. So this is what you call, let me have this. This is the outer casing. And if you have actually had a chance of looking at an everready as a primary cell, you can have that red outer casing. And just below that, you can be able to have what you call the gray zinc casing. Okay. You can later be able to have this as our graphite or carbon, and literally we need to have this. Okay, so this must be powdery mixture of carbon and manganese for oxide. Outside here, we need to have this. So we have here what we call molten zinc chloride and ammonium chloride. Molten zinc chloride and ammonium chloride. And this is what we call the brass. Brass consisting of zinc and copper. Cap. And this is an insulating material, just at the top here. So we've said this is a primary cell, and primary cells are also referred to as dry cells. So a primary cell can also be able to get called dry cell, or a good example is a dry cell. And the most common cell that we have in our environment, in as far as a primary cell is concerned or a dry cell is concerned, is called the clanche cell. The clanche cell. So you can call it a dry cell or a clanche cell, and this is a very good example of a primary cell. You said it is non-rechargeable or cannot be recharged. Once it has been used, it gets discarded when all the energy in it is consumed. A drawing of this cell is here. And of course, this cell can get used in torches, watches, clocks, flashlights, electric bells, radios, calculators, and then the remote controls we use in our homes. The maximum this cell can provide in terms of voltage is 1.5 volts. This is its power output. The much it can produce is 1.5 volts. And of course, if you look at its outermost casing, it may have different colors, either red or blue. This outermost casing will just enclose the cell and further protect any damage to the zinc casing or prevent zinc from reacting with any chemicals within the environment. So the whole cell is protected by this outermost casing. It looks like plastic or paper, you see. And just below that outermost casing is the gray zinc casing. The gray zinc casing will act as our cathode or negative terminal of this cell. Our cathode or negative terminal of the cell. So it serves as our cathode or negative terminal of the cell. Our cathode or negative terminal of the cell. And this graphite or carbon will serve as our anode or positive terminal of our cell. So the graphite or carbon serves as our positive terminal or the anode. And just around this graphite or carbon or the anode or the positive terminal is a powdery mixture, a mixture of carbon and manganese 4 oxide in powder form. And of course, the work of the carbon is to increase the surface area of this graphite so that the graphite or the carbon that is serving as the anode becomes more efficient or effective. And this is facilitated when carbon in form of a powder is allowed to actually surround this part. So our graphite or our carbon is our anode or our positive terminal. To make it have a larger surface area, to make it more efficient and facilitate these redox reactions occurring, we need to add carbon in powder form so that this surface area is increased. Just within this environment is manganese 4 oxide. The work of this manganese 4 oxide is going to actually get given in the next few minutes as I'm actually proceeding with this discussion. At the top here is the insulating material. This prevents the flow of current to the outside, to these unnecessary regions within this cell, so that current can only be able to get allowed through this graphite and through this brass cap to the next cell or to this electric device that is getting powered by this cell. So the insulating material, and of course an insulator is a poor conductor of current or even heat. So that means whenever this insulating material is here, it prevents the flow of charges to these other surrounding regions. And current can only be able to get allowed through this brass cap to the adjacent cell during this arrangement, or to this device getting powered by this cell. And the brass cap we are having here, brass is an alloy. An alloy is a mixture of two or more metals. You can talk about brass, bronze, you can talk about duralumin, that consists of magnesium, aluminium, you have what you call manganese, you see. And that means brass will consist of zinc and copper, and this mixture, being a mixture of metals, will make this area very effective to transfer current to the adjacent cell or the device getting powered by this cell. So this mixture of these two metals making up the brass can allow current to pass through this region, so that this current can get delivered to the next cell or to the cell next to this cell getting discussed here, or to the device getting powered by this cell. The electrolyte in this cell is a mixture of zinc chloride and ammonium chloride. This mixture must be in molten state or in form of a paste. And we are saying that every cell must have an electrolyte. So the electrolyte getting used in this dry cell or this primary cell is called zinc chloride ammonium chloride mixture. And this mixture must be in form of a paste or must be in molten state, so that the ions are mobile or delocalized or free. I don't expect if zinc chloride and ammonium chloride as a mixture being solid state can even end up allowing the flow of current, allowing this cell to provide current. It cannot. In solid state, we have strong forces of attraction holding those ions together strongly. And if the ions are not mobile, no current can get generated when chemical reactions occur in this cell. Okay, so the molten or the paste, where you can say the paste form in which this mixture needs to get used, is to facilitate the ions in them, and the ions in it to be in mobile state, or to be mobile, to be delocalized, or to be free, so the free, mobile, or delocalized ions can be able to allow current to flow through them. Okay, so what happens? We've actually said that we need to talk about the cathode in terms of which chemical reaction occurs there. At that point, zinc dissolves, and in the process, it actually gives out two ions or two electrons. So the zinc can that forms the cathode is able to dissolve, and it actually ends up giving us zinc ions, where electrons are actually given out. And at the anode, we expect that the ammonium ions, where are these ions coming from? Remember, I've told you that this mixture is in molten state. So expect to find in zinc chloride, zinc ions and chloride ions. In ammonium chloride, you expect to find ammonium ions and chloride ions. So at the end of the day, the zinc ions can add on to these ions getting formed here when the zinc dissolves. And these ammonium ions are able to gain the two electrons lost at the cathode. Okay, so they can be able to form ammonia gas and hydrogen gas. So at the cathode, we have the zinc can or the zinc casing. This dissolves to give us zinc ions and two electrons are lost. At the anode, we do expect to find one, zinc ions and chloride ions coming from the zinc chloride, and ammonium ions and the chloride ions coming from the ammonium chloride. The ammonium ions are able to gain the two electrons lost by the cathode to give us ammonia gas, then hydrogen gas. These gases can actually accumulate at the brass cap, inhibiting the flow of current or lowering the efficiency of this cell. To prevent the efficiency of this cell getting lowered by these two gases getting provided, what happens? The manganese 4 oxide that had been mixed by the carbon in powder form around this graphite will oxidize this hydrogen gas to water. Hence, hydrogen gas is actually eliminated or removed. So, the work of the manganese 4 oxide is to act as an oxidizing agent, and it oxidizes the hydrogen gas getting produced here to water. So, hydrogen gas gets removed. Then, this ammonia gas that remains here will react with the zinc ions from this mixture, and the zinc ions getting formed from this dissolving of the zinc canning or the zinc casing, so that we can be able to form a complex salt. How? The zinc ions from the zinc dissolving and the zinc ions from the zinc chloride paste will actually react with the ammonia gas getting produced at the anode to give us a complex salt. And this is our complex salt. It is called tetramine zinc 2 complex. Tetra for amine zinc 2 complex salt is formed. So the ammonia gas is eliminated. At the end of the day, hydrogen gas has been removed by the manganese 4 oxide acting as the oxidizing agent, and the ammonia gas has been removed by the zinc ions, which react with it to form a complex salt. At the end of the day, this cell becomes more efficient because 1, it is cheap, and 2, the electrolyte getting used here is in form of a paste, so no leakages are recorded at the end of the day. 1, the cell is cheap, it is affordable. 2, the paste or the molten state of this mixture serving as our electrolyte will not allow any form of leakage to occur when the cell is in use. Thank you so much for your time. Hope you've actually gotten something, and let's meet in our next lesson.